All right. We continue with the last talk of the conference. So it's a great pleasure to introduce Ilia Zharkov from Canada State, who is going to tell us about Lagrangian SYZ Fibrations.
All right. Well, thank you for the invitation, giving the opportunity to speak. And since I'm the last talk, maybe we should thank the organizers. Okay, now try to finish in time because my flight. Okay. So, all right. So, this is a joint work in progress. We didn't write down all the theorems yet, but we're pretty sure that we can prove the final statement here. Check your mark, Diego Matessi and Ilia Ruddat. As I should probably be in application for this couple of slides everybody is familiar with. So, strange real made this probably wrong conjecture, but it was very inspired. So it's a good conjecture, inspiring to think about it. So we have a mirror up here, and they both have special advanced vibrations and map to the same base, and the fibers are dual torus. Of course, the question is well, everything is fine, except what we start worrying about what's going to happen at singular points. That's where it's probably going to be wrong. So the reformulation, which right, was done by Matessi and H a couple of years later. So they considered the statement of the special interpretation in lineage, and the formulation they gave is to look at a fixed scalar class and scale it over the diameter still fixed, and then take the limit as go to large complex structure, and then sort of use the whole to collapse to complementional space. And so I think they were the first to actually say what we expect about this singularities. Okay, all right, so they can have to be in ST2.
It may have been pointed out. Several people actually consider Solomon. I think probably the Ross and Wilson had actually proved something for these weeks.
I think they proved it later, probably at the same time.
Yeah, I think they were both different, but Ross and Wilson actually proved something.
The statement will take place. Yeah.
I think that's true. In my mind, that's also.
Ross Wilson certainly probably actually proves it. So when the proof was a base theory, this correct. The conjecture with a metric, so there is also metric involved. I didn't write this for it, but from what I'm going to take from it is just a base integral by manifold with singularities in dimension 2, and then sort of tangent and cotangent bundles naturally over the smooth part naturally have one has a complex structure, the tangent bundle has a complex structure, cotangent symplectic structure. We expect sometimes both of them to actually compactify to the actual LDL we started with. And this is what I'm going to talk about. First, let me mention that the complex thing does not compactify it. This is where we do all these corrections can come from discriminant. But the symplectic side, I'm going to show you how to compactify. I think this is needed. All right, so the question is, you can pose backwards or start with the base, how the elements are. So that's a big work of the rest of the part. Plus, I don't know, did I put the date approximately correct? 2004, 2008. Anyway, right, about Lagrangian. So they added some conditions on a base, namely some polytopic decomposition of it, and some gluing data, some sort of class in this how you view the different torus strata, and then some assumptions for on singularities which cover all the varieties or complete sections. So it's a pretty general class of singularities, and then this space. So if you take this bunch of minimum toric dividers, toric varieties, then this is a loss. This is an amplified scheme. This is the loss structure given by this data, and then well, I just spoke with Bernard this morning, and he said that the word often in a stock paragraph should be always. But in any case, so sometimes the people say often it does correspond to some actual analytic family. And in this case, we can look at the generic member of this family and say, all right, this is our Liouville. In any case, the generic member is homeomorphic to the so-called Nakayama space. You can construct without any just from block. This is a topological space. And we expect that topological space, at least topologically, should be our pop-up identification of that text. So I'm going to work only on the cotangent side. The problem with this Nakayama is it does have a natural map to the base, but it has singularities, not in codimension. Right? One, a little sticky. Okay. So let me say a word. This is a little dense slide, but I have to say what's the singularities I'm going to consider. Because unfortunately, the word simple was taken by the growth of Ruddat, which is actually not that simple. So I'm going to go very simple. So it's really very simple. I mean, it can be simpler than that. So we have a manifold B. It's a certified space, and we have a certified subspace which is discriminant, and so it consists of a bunch of manifolds connected to each other below a stratum. And for each stratum of the D, we endow it with a certain additional structure, namely we take two polytopes, actually two standard simplexes, to provide very simple. Two standard simplexes, one that we mentioned M, which lives in invariant tangent subspace, invariant tangent lattice, and the other is a dual, is a standard simplex in a dual, invariant cotangent lattice. And the condition which we want is that if you go from a larger strata to a smaller strata, then the polytopes gets larger, and as we go from a smaller strata to a larger strata to a smaller strata, the polytopes on a larger strata become faces of the polytopes. So like if you have dimension, you have a dimension 3, you have a graph, you have edges and vertices, and usually over the edges you just have a pair of intervals, and over the vertex you have a triangle and a 4 interval and a triangle. From the different purposes in dimension 3. So once we have this data, then there are actually more combinatorial data which we need for the construction. So first of all, topologically, the neighborhood is just the standard picture. If you have a y called y, but if we have a triangle, there is a normal plan to this triangle, and then we take the two-dimensional skeleton of this triangle, of this normal form. So this is what I call y. Delta. This is y. And the same thing for the delta. Oops. Oh, what? I'm sorry. Yeah, let's do that. But there's more actually here. So I actually want, so for delta, I want a fan which is what I call integrally transversal to delta. And I think this is so if I have a delta, so the fan which I want, I mean the normal fan doesn't make sense if you in the space, but I want a fan in the same space. And the condition is that whenever I put it the vertex in, it has to intersect all the faces of my simplex transversally over that. So this is an example of an F. It doesn't have to be strongly convex, but it can. So, and that's going to be the shape of a possible discriminant. So, as I said, so this is an additional discrete data. The different Symmetry F will have different local models. And I think I've tried to compute actually the number of those values. It's something like n to the n or something. I mean, it's a finite number. In addition, one more additional data, which you'll see on the next slide, is the choice of the fan check, which is kind of a normal fan, but the normal fan lives in the closure space, and this somehow actually lead to take a section of it. And I'll show in the next slide. So probably maybe I'll show it here. Yeah, let me show the next slide. And of course, there is a condition monotony, which is the standard one. If you go around the maximum circle, then this is essentially identity with one non-zero element. That element is precisely this one. So if you look at the gross Ripper papers of what that should be familiar. So in gross Ripper, they consider more general case when you have several test polytopes, and they are not necessarily standard sequences, they are elementary sequences. I think that the theory which I'm going to state is true for this case. Also, we don't even need elementary because we need sequence. And then you can take some color. All right, that's the picture I was trying to show. So on the left, on the right picture, that's the picture of the fan F, which is transversal to delta. And if you look, okay, so this is a three-dimensional picture. So on the right, you have what's called negative vertex. When your discriminant lives in an invariant plane. And so where is the fan F check? The fan F check actually enters, how we bend this, they're all in the same color, but I've tried to make them kind of this brownish color for F check. So we have actually two things. And there's, if you think about it, there's actually Z square choices. Because we can always fix one of them going down, but then the other one we have a Z square. So that all are all different discrete data. You don't see it in terms of the discriminant in this case, but you do see it in terms of the discriminant for the positive vertex, which is the left picture here. So for the left picture, you have this open book thing. And then your discriminant sort of looks like this. And this is again, now there is a Z choice of this pattern. You can always fix this rate to be whatever you want, but then this third one, if you can do it like that, you can do it like that, you can do it like that. So there's a Z choices for that. So in general, the number of choices is the lattice spanned by delta. And I said the word, so the keyword here is modeled. If you see, so relative neighborhood is modeled. So modeled means the following. So again, in this picture, I do not necessarily need my discriminant to be exactly like this, but I want it to be, at least this is the way how we cannot do it better, and we want to make it sure that it's tangential. Yeah, so discriminant maybe not necessarily straight, but it has to be tangential. So this discrete data at the vertex itself, it still remains as a discrete data. And this seems very artificial, by the way. So, but the way how our construction goes, we cannot, make it all, change the direction as we go there. And I will try to explain. So that's my theorem. I'm trying to convince you. Okay. So given the integral affine manifold with such a very simple singularities, you can actually compactify to something which is a smooth symplectic manifold, and with a proper map to the base. And when we restrict to the outside of the discriminant, we do recover the original cotangent torus fibration. And the fibers, all the fibers actually are equidimensional in the sense of pure dimensional. So they all, right, all the maximal strata in the fibers are three-dimensional or half-dimensional. And the second statement is that actually is homeomorphic to the Nakayama space. So today's morning I talked to that. So their construction also comes with a symplectic form. I mean, it's a polarized thing. The question is whether we have symplectic model or not. So this is a new question I just start thinking about. And
well, do you claim that's unique?
No.
Is there a minimal one?
Minimal means what? Okay, there's a question.
Minimal model.
I don't know what minimal one is. I think they're all equal rights. I mean, there's no
But you can blow up. That doesn't,
I've changed the dimension of the file. This is a Lagrangian stuff. We are not blowing up anything. B is fixed. Discriminant is fixed. But discriminant has this discrete sort of parameters which Gross and Zibber did not have. So I'm worried if it's for this. We may have a different. Of course, if you vary the things continuously, then it's the same symplectic manifold. The vibration changes, by the way. Vibration depends, maybe the same symplectic manifold, but the vibration depends on what particular discriminant you have and everything. Of course, it depends. So
you can prove that but your models, depending on the choices, may still be symplectic. You don't know, but the vibrations.
I don't know. Yeah, we didn't. This is the first 2 hours ago. This is the first time.
No, that's just forget it. That's human.
Yeah, this is.
It depends on choices.
You asked this question to me. I was expecting more, and then I started thinking whether our choice is either. It's a very good question.
So one discriminant will be the same.
Same discriminants give the same.
It's okay, but can it be different?
I don't know. It's certainly different. It's maybe it's the same symplectic manifold. They also maybe of course, if you read those, it's the same symplectic manifold. You continuously nothing changes. I don't know. It's an interesting.
The space is topological, but that always has to come down.
Topologically, it's always the same. It doesn't. Yeah, with all this.
You're worried that you need that topological.
No, topologically, it's always the same. It's always homomorphic. Okay, so I'm gonna go over depending on if we get bonus or not. But I want to show how to look at the low. So okay, so the consistent of course we need local models, and that's the cornerstone for everything. If you had a local model, you would be able to do it long time ago. Doing is just some technical. Local models is a cornerstone. Think that then I'll do a couple of issues, play a couple of issues with viewing it. And then if you have time, then I'll schedule what's the single plan. All right, so first let me start with some basic examples. Everybody knows and love no discriminant. The world is wonderful. There is a unique symplectic manifold with a unique Lagrangian fibration up to symplectic 1. This is the armor. I put this one just in case. Next case, when you reckon that the simplest possible singularities are 2 with a origin and the monodromy given by this here. And again, this is a very simple case because we do have a kind of a stupid Lagrangian fibration, and it's just mapped by the log and a moment map for the first two provided. And this is Lagrangian, and now the question is of course, okay, now we actually have non-uniqueness. If you require your fibration to be your map to be smooth, then these are classified by NDOC, and they're classified by form of our series two variables. If you don't require to be smooth, I don't think it is good. By the way, in this theorem, I do not claim that our map I is smooth, because as you'll see that we have no control over the dimension. I think dimension 3 don't have over it. So, and the point is you can easily add more variables x, y, z, and so forth. The same vibration would be done. So, in case when you have one W on the right hand side and all of them on the left hand side, and then it's actually very similar. The first example, first non-trivial case was done by Evan Smollery a couple of years ago. They did a negative product. If x, y equal 1 plus W1 W2. And this was actually the history of this thing. So we started this theory working on this topological thing, trying to compile topologically. But then already we did it. And we were kind of already writing this down. Then okay, now we ask, okay, we have this topological space. Does it have anything to do with the actual world? And that so can we put like a smooth structure on it, symplectic structure on it, and then Mark Gross pointed out in this paper, so we actually dropped our original topological thing, and now we are. What does negative voltage mean? It's this. Well, the model for this is the xy equals. It's a dimension 3 when you have yeah. The picture for the negative vertex is you have something like that. So you have an invariant plane and then you have a spread variant discrete invariant plane with the standard monodrom is in the form 1, 1, 1 and then. It doesn't mean okay. So this is a simple example. Let me move to the how we're going to build the local model for the general NMK. NMK means so okay. Maybe I'll show it. For those who don't know what do it like x0 dot xk equals 1 plus W1 plus W2. Yeah. That's going to be the roughly speaking equation for the local model. Okay. All right. So let me start with some combinatorics again. So again, this slide is pretty much a lot of combinatorics. Lots of choices, but we start with W. W is a base. Draw it. I think I'm drawing it on that. So this is case 1-1. We have a base, which is a product of the Rn. So this is Rn direction. And this is like marking the 1. So the boundary of this H is going to be my base. And all right, so where are the fans? So the fans, I take the standard fan in this thing, and I take so here is my F prime. I also have the F in Rn thing. And now the question is, where do I have my okay? So for the F, I explain my choices. This is also the simplex of delta and f of both here. And suppose I have my delta. All right, so I'm going to extend the delta a little bit inside, so add the vertex kappa here. So this vertex supposed to be inside now. I'll have a next slide. Okay, so and the question now is, all right, so what's the choice for the f prime? How do I see the choice? And the choice comes from actually putting a affine structure, one complement. And that affine structure depends. So then we usually how we put affine structure, we look at this coordinate subspaces, natural affine structure on there. But how we put affine structure in a complement of f prime? Well, we look at the k, the vertex k, and kind of start projecting from k to different different quotients, and then actually, if you project from this vertex or you project from this vertex, you see that the f prime ray is going to look. So this is the standard focus case. So this is f. No choices for the f in this case, but the f prime actually has a choice. So you can have f, or you can have this, or that. So there's a choice for the f prime, and that's equivalent to where we put the vertex kappa. You always have, the b coordinate is always 1, 1, 1, but this choice for the kappa 0 is equivalent to the choice for this discrete.
Here are four questions. Dimension 4.
Yeah.
There are a lot of log transforms that take out of the symplectic world, in particular Fox surface. So why does that not happen? Yeah.
I don't know. I didn't think about it. So maybe there are different bases. I'm not sure what does this transform does. It probably does something to it. Because I mean, it changes the piece of blocks, right? So it changes the triangulation. Yeah, it changes the discriminant. Anyway, so there are many questions which I don't know the answer to. So this is pure symplectic thing.
So there is something that has to be received. We see the affine structure.
Yeah, I mean, that's
yeah. You change the whole species. Yeah, that's different. Like even in dimension 2,
but so what does contradict your something? Why it doesn't give us something meaningful identity for all this?
Because this one is torus.
If I have a base, no discriminant, I just take the cotangent one. All right, that's the picture I was trying to show. So on the top left is my wedge, and I need an okay on the top right is how I get my fence, and I need additional structure. This is a kind of auxiliary, so this is what I call this is polytope. Well, it's not a polytope because we're not in Rn, we are in this monodromic kind of thing. But we can still make a sense of polytope. We can still make sense of the hyperplanes there, as long as we are contain some parallelicity to the invariant spaces. Then, for instance, on the right, you see this trapezoid kind of thing. It's a square in some sense. So all the edges actually are straight lines. You see the right edge not being straight line because you can look at it in the wrong chart. So that's my polytope, and once you have the polytope on a base on B, then there's a unique way you can lift it to the W. And the picture maybe I was trying just to leave me to draw it, maybe it's not successful. So here you have your polytope P, and here you have your simplex, And there is a unique way you kind of link the walls of your polytope to one dimension higher, staying parallel to the corresponding traces. I'm going to call it A for H. Okay, now, all right, this is combinatorial data. Fine structure and everything. Now we need a space. All right, so wait a minute, you could with a space, or okay, of course we start with a toric variety, as you know, which correspond to this page, which is just you know, C to the power k plus 1 times the C star as a symplectic. Right, we don't consider it as a complex, just a symplectic. So there's a unique symplectic form which kind of you know comes from the historic construction, which essentially you know given by in this dual coordinates given by the you know this pairing the coordinates on a base with the corresponding dual coordinates on cotangent fibers. And that extends to the boundary. So no problem with that. Now we want a hypersurface in there, but we want to make this hypersurface inside of it is symplectic. And probably the easiest and probably the only way to see something is symplectic is actually to see that it's sort of holomorphic. This is I think the idea of Donaldson maybe used many times, you know, by Zaid and other people. So sorry, what was that? How do you show that subspace of a symplectic space is symplectic? So the idea is this, I think Maxime may be talking about that actually. So it is compare the holomorphic part with anti-holomorphic of the map of the tangent model. And see that if the holomorphic part, for instance, is much smaller than anti-holomorphic or the other way around, that actually makes it simpler. So the shows that yeah, I think this is one of the papers. Technique with the symplectic homomorphic section, which is different from what one saw. But the idea is to compare the deep part of this deep bar. Yeah, but inequality. So in any case, what he shows is that hyperplane section for big enough torus, the sections of the long bundle, with big enough degree, the hyperplane section is a symplectic submanifold. Yeah, that's what it's shown. Yeah. But anyway, so we want some complex structure. The complex structure, so we get a complex structure, we put the potential there. And the potential actually gives us the complex structure. If I think this is probably usually human, if you have such an asymptotics at the boundary, then and this is an if and only if and G some smooth function, then it gives the Taylor potential. Yeah, so this is what I said. So if you have such a function, such a convex function on your base of your moment map, the symplectic, so you get a complex, but you get a complex structure, you need such a potential, and then you get a you know, torus invariant Taylor structure on a thing. And the complex coordinates, okay, they have very general for the log part, log coordinates are very general the original coordinates, and we just keep the data. Okay, you can also view this thing as you would start with this complex manifold, C star to the n times C to the k plus 1, and then you put a potential over there, and then, but that's equivalent if you just sort of replace your P by the Legendre rule, and then you say, you know, minus dc of f will be your Liouville form, and minus dc is your Taylor form. Okay, and now we're going to look at this upper surface thing, which is given by this equation. And again, so there are these cutoff functions, beta, which everybody wants to use because it makes life easier. You have more torus action in certain regions. And if you move, if you kind of make them go to zero if your term w to the power is already small, then so that does not destroy the holomorphicity too much. So that's symplectic. I think this was carefully discussed by Abu Laintin. This is okay. Okay, so in particular, this is like everybody knows this way. When beta, as I said, so beta go to zero when the monomial is already very small. That does not change the image. Oh, okay. And now comes the key. I think this is the key result here. It's very little technical. So I'm going to particular type of potential. Okay, I have asymptotics, but I want more. Actually, to run my construction, I want my hypersurface to become a product of the lower dimensional hypersurfaces with some C stars. And for that, I need a particular condition for my potential. So again, so I'll write it over here. It's exact statement, but probably I'll show next slide what I actually mean by that. So first of all, I'm going to root. I don't want the full wave, because in full wave with the problem, I'm going to root. That's a rooting. So like in next dimension, the root, if you have a corner, then you can root it like that. So that's what's left. I don't want to give them the here on the street on the that's problem for convexity, for instance. So in some sense, all my weights becomes very, very close to just the boundary. Just a little bit thickening of the boundary. And I just want to do this so that my hypersurface actually lies inside, so that does not affect. And then I have this conditions for vanishing some certain mixed partial, which I will try to explain why it is important. And this is actually not easy to do such a potential, and that's I'm hardly know how to show it's convex or only strict convexity. But I think we managed to do this, and let me explain what's involved. First of all, what about the cutoff function? The cutoff function are let me maybe show it on a picture here. So here we have this 1, 2, 3, 4, 5, 7 regions here, right? Inside the triangle, we don't require anything. But if you go towards certain infinities, we want certain partials, mixed partials to vanish. And I'll explain why we want this. So, for instance, I've shaded this domain here, which is tau plus some multiple of tau plus this corresponding transversal cone. So in here, what do we want? We have, in this case, we have this cutoff functions for A, B, and C. And of course, C is kind of far away from that. So we don't want any monomial which is associated with C. So we just set it to be 0. We want it to be 0. So we have only 2 monomials here, A and B. And for those monomials, we want the change, the function actually changes as we move from left to right. But this change we would like to be, kind of parallel to the vector mu. So it's only changing. So the mu executes this change. So that's the left-hand side for the cutoff function. And the potential itself, well, so in the straight reason, we have 2 monomials, A and B, and we want those to be the mixed partials of the potential to be 0. And I'll explain in the next slide why do we want this. So before that, let me explain that once we have this thing, this decomposition into domains there, we can actually choose our polytope domain kind of large enough so it has the right thing. And maybe I'll just show you this is my address this morning. So I don't know how useful this thing is, but you see, the blue is my decomposition of R3 into regions, and the red is my polytope, and I would just like to be big enough so that it hits all the regions where it's supposed. And now comes the so Ruddat said there should be a proof. So if we have this, then what happens is actually that we have a product structure in this regions. In different regions we have different product structure. And okay, this is what I said. So this torus is the normal torus to the base where we have the action. We have the action of this torus because we have no monomials which are not invariant with respect to the section. We rewrite our hypersurface in this form. We pull everybody on one side, and then it's at this form. You see that this hypersurface is entirely in the moment coordinates. It has nothing with a log coordinate. It's entirely in the moment coordinate. It's a hypersurface purely in terms of the moment coordinates and theta. It's a complex equation, so it's a codimension. Okay, and then if you look at this equation, then you see that these conditions which are on the previous slide, they precisely make this hypersurface invariant. So, all right, the ambient space, whenever you choose any direction and any transversal direction into the transversal, you can always split your Liouville form into the sum, right? Because you remember your Liouville form is just u times dual d theta, right? So if you make sure that u and theta are dual, and you can always do this once you have an integral transversal thing. This is the first statement. So out in the ambient space, you always a product. Now the question is, we have a hypersurface inside. Where this hypersurface is a product? That's when the equation of this hypersurface is invariant both with respect to this torus section and with respect to this extra direction of this kind of radial direction of my ceiling. Okay, so proof. All right, now comes the idea of Evans-Mowry, which is kind of not very hard, but it's a very nice observation, which has the following meaning. So if you have a Liouville domain, you look at its contact boundary. Then, of course, if you remove the skeleton from your Liouville domain, that's the symplectization of this compact manifold is electromorphic to the original manifold minus the skeleton. So it's the same manifold, and then we just add the skeleton. And now, all right, that actually gives you the way, once you have a fibration on boundary, it's also fibration on boundary, you can just take a flow, you will flow everything towards the skeleton, and then give you the vibration over the inside. So we don't know what's going on inside. So this is the picture to have in mind. So to have a base, some base, and then we have a vibration over here, everywhere over here. We don't know anything over here. But what we do, we just flow everything, cone-wise inside, and that gives us the vibration, the Lagrangian vibration over the entire thing. And then what do we have over the vertex? Over the vertex, we have a skeleton. That's what's left. Now, why the product structure is helpful? The product structure are very helpful because now we can run the induction. I'll draw the focus case where we don't need any induction, or to draw anything else. So here is our polytope. And by induction, we have a vibration over here, which by induction has actually a T2 vibration over here. So this is in this region it's T2. This region is T2. Here it's T2. Here we only have S1 action. S1, 1. So what we're going to do? Well, we're going to use our form construction actually to flow everything to form. So now we actually, the next step, we actually have a T2 fibration over everywhere. We have a T2. The key point is the cone construction. If you have a product in a neighborhood of, if you have a product over here, the product over here, if you have the product here, if you take the cone, it actually doesn't change. The product structure, the cone respects the product structure. So this is actually very wonderful. In the sense that we had a product here, we took the cone, we might destroy something here. So this actually is not compatible with this one, but we don't. So we actually have the same T2 fibration we had in the corners, we just extend it over the inside, and then we flow everything inside. So that's roughly the idea of small range. But as I said, so first of all, we need a product to make sure that we don't destroy anything. And second of all, we want, which boundary do we take? If you just take, this polytope thing, it's not smooth. It's not a contact boundary. It's not a manifold. So we kind of cut the corners a little bit here. And it doesn't matter how we cut them because we have a product. It doesn't matter if we cut it like this, or we cut it like this, or we cut it like that. It's a product, so the cone actually would not depend, taking the cone would not depend on where particular boundary we took. Okay. All right, so there are a couple of things about gluing, which I want to maybe point out. The first program, maybe I'll show the slide because they made wonderful picture. Sorry about that. You have this products now, right? So you have the reduced space, and then you have the your transversal cylinder. But now you're trying to glue, these two models together. There are two problems. What if the reduced space actually are not parallel, right? So remember there was some choice of this polytope poles. Where is the choice up to? It's the choice up to this tilting thing, because we still want to be parallel to this delta, to this edge. But red or blue, that's a choice. And but that's luckily, if you make one choice, it's a product. There's actually a way to make it the other choice and still be a product. And this is what we call tilting. And this is done very simply. We just why there is a choice? Because there is an additional global, TK action. Because we have this XYZ thing on the left, so we have a global TK action, and that's precisely our choice. Which of those, tori we actually act by, and this choice is up to this TK action. So we just adjust this, this TK action here. So we just add, this action of the TK on previously not acted to this action of the cylindrical factor, and that effectively does the tilting. So tilting is the first thing, and now weaving, tilting and weaving. So we have this discriminants, right? So far we know how to do the product thing. So we have the product. We have this picture over here. Maybe I'll show the next picture. See, so we have something from the left side, and then we have something from the right side. And there is some discriminant in between. We know we start with a straight line. This is how we know how to do it, because the straight line is a product of the focusing times the super cylinder. We don't want a straight line to be our discriminant. We want our discriminant to be whatever it is. So how do we do that? Again, it's very simple. We just, in the reduced space, the number of the first cohomology, closed rank cohomology, the dimension of the closed rank cohomology is precisely the dimension of this delta. So, oops. So we just add for each direction we would like to wiggle, we can find some closed form in the reduced space and just add it to our Liouville form. It changes the Liouville form, it changes the symplectic structure. but still the fibration is still, so fibration is still Lagrangian. That's all we care about. So we locally in the street, we change the symplectic structure from our product one. It's not a product anymore. We change the Liouville form, and once we change the Liouville form, that effectively changes the action coordinate and the integration of the Liouville form or cycles. So that's the wiggling. We can wiggle, and again, the problem which I'm personally not very happy about, can we wiggle all the way towards here? Well, at the moment, we actually have to stop at some point here, very, very close. We can probably wiggle all the way, but tangentially. And that's very meaningful. So wiggling. So we start over straight. This is our local model. And now we kind of cut the thing, and then we wiggle inside as we like. Because this is like this. See that? This is the we just cut it, wiggle, and pull back our new symplectic manifold. And then we start extending over the outside. So that's the thing. So we start the vertices, do the edges, do the faces, and so forth. So that's the induction thing. We can go all the way to the vertex, but as we go closer, there is less and less room for the wiggling because it becomes kind of thinner and thinner. Anyway, this part we actually didn't try down yet, so I'm not exactly sure how or whether we go all the way down. We can certainly go to just any epsilon, but whether we can go all the way down, that's even if we do, I'm not sure that we can change the tangents. Okay, that's my wiggling. And maybe on the other end, you actually have a different direction. That's again a wonderful thing to do. So we don't have to have the same direction on both ends, because once we wiggle by the integral number, then we added the integral form. If the form is just an integral form, then it's again a product. It's a product with a different cylinder, but it's still a product. And that we can match it with the other product. So that means that if you wiggle, and then eventually we go, for instance, a 45 degrees change of direction, then we can actually glue it back to the right model with that given direction. All right, I have 7 minutes for bonus, so it's plenty. Let's now, all right, let's everybody is of course interested in particular fibers. What kind of fibers? Right. So the fibers, as I said, so they are the skeleton of the cone construction, so they are just the skeleton of this local model. It's a fiber now. So let's try what can we say. Let's try to see what can we say about the fibers. In our potential, kind of very, very symmetric. So the way they build, they always going to be in the following form. So if you have this model, we have so we are okay in the very middle of the simplex. We don't very any there are no border betas are actually one, so we actually should have two complex factors. X0 x k 1 plus double 1 plus double inside close to the skeleton. So we can just study this equation. And all right, so our potentials are kind of good in the following sense. So we always have one critical torus, which is TK torus, which is, so here we have pair of pens, which is this guy equal to 0, pair of pens. And outside the pair of fence, there's only one critical. It's not a point. It's a Morse mod. So they have a whole torus. But it's the index n. So we have this torus. Then we attach the disk, the n-dimensional disk, and the boundary of the disk glues to the skeleton of the pair of fence, which is n-1 dimensional. And this is the n here. So glues. There's the Sn-1 on the boundary where the torus collapses. So this torus becomes more and more and more, and then it finally collapses. So we have only the sphere and the boundary attached to the skeleton of the pair of fence. So this is a general picture. It doesn't matter which particular. I mean, it doesn't matter to some extent. Sometimes we actually have ugly stuff. If you take some stupid function like a distance function, you actually have more than one critical torus. So in particular, this is an example of the cross which everybody likes. Right? So we have a pair of fence. We have a skeleton here. Nice skeleton for a pair of fence, and then you have, so if you draw the skeleton in T2, then you do like this. And then away from it, you have a circle times the disk T2, and that boundary of the disk. So in some sense, that disk is interior of the zonotop, and then glued to the skeleton. So everywhere over the two torus, you have a circle bundle, except over this figure theta, letter theta, place where the circle blocks. So the standard picture for the histopologically people like most. So we will try to do the same thing in higher dimension, and that's where it becomes complicated. So everybody loves this thing. This is called interpretation. The question now is what's the skeleton on the pair? Everybody loves this tetrahedral skeleton. I've tried to okay, the left top picture is kind of irrelevant, and so is actually right top picture. But so this is a two-dimensional pair of fence, and I've tried to do the this green thing is a zonotop. The complement of that is a colonial, and you see that the black thing is the tetrahedron. So it's a boundary of the tetrahedron, which is everybody's favorite skeleton of the pair of fence. So, and on the right, you see kind of how this thing stuck together into the color. That's the goal, that's the dream. And the dream cannot come true, at least for this type of thing. Gamash and Nadler actually claimed they have this skeleton for a pair of fence. Was trying to get it from the, or they get it, and there's some complicated lessons, fibration. I don't understand. Certainly not with the potential you have, we can get it. Now, okay, that's my favorite. That's my favorite potential so far. This is called Softbox. Okay, I'm gonna now work in a lot coordinate, so I transfer everything to the horizontal dual function. So that's my function. I'm going to look at this function. Again, this is not complete in the sense that if you just look at this function, it will flow actually. This stops. But since we are, we can always complete it by adding for quadratic terms, so that's not a problem. And this is my favorite. I spend lots of time actually computing it. So I computed all of the gradient flow and everything. Some computation. But the result is that I actually like it a lot. So if you just project this, all the flows and everything, all the critical points, all the real points. It's kind of not hard to see. But we want the minimum kind of skeleton. We want at most one critical point wherever you go. And that happens here. And if you project everything into the torus, into the coordinate, then the gradient flow is actually equal to the gradient flow of the Pauling Morse function on the torus. It's a nice function, and show it.
So there are some parameters involved, the alphas, so the sum of the alphas is 1, so you can take a polygon, take the edges, each time to 1. It's a wonderful space, also study. I had another hour for the last couple. And now let's look at the function. So I'm looking at the disk, so all the functions alpha 1, alpha 2, alpha 3, alpha n. It's a homogeneous thing, so it's actually n plus 1 of them. But the function is well defined because if I change the theta, they're also homogeneous, so they're up to the common rotation. So that's the function. This is between the beginning and the end. And now you can play, the story to see what's the critical points of this function. Then start pulling, and boom. That's a critical point. Everybody see this? It's critical. It's even click. It's a critical click. It's a critical point. You see? It's a real point, right? So all of them are, either plus or minus, same command. And then you just move a little bit in the right direction. So then, well, if you move it carefully, then you start pulling, and then it's click. That's another critical point of high end. And as I said, I'll stop here, but I've studied this space a lot, so it has a nice, very nice CW decomposition. Everything is completely explicit, depending on how far it changes the topology and everything. But it never gets a certain technical. So this is unfortunate. All right, so I'll stop here, and thank you.